off of our introduction to clustering and just talk about how we can implement the k-means algorithm computationally in Radiant. This, I think, is actually going to be quite easy for a lot of you, but we have to remember the algorithm and a lot of the things we learned in the previous video sort of in the back of our minds, and that's going to help us sort of diagnose what's going on and make good decisions from the results that we get. So I promised you a nice little picture of how the k-means algorithm works, and I think this one does it quite well. So if you remember the k-means algorithm, first starts with the data sets like this. So this top left-hand panel, it's all black, right? We've not assigned any clusters yet. And then step one, we randomly assign everyone to one of three clusters, right? In this case, we have pink, orange, and green. And you can see it's quite random, and these clusters look really bad, right? But that's okay. So what does the next step of the k-means algorithm tell us to do? Well, it tells us to compute the centroid of each one of those clusters, so of these random clusters. And it does that, and we can see that in the third plot, so iteration one, we can see that we've computed the centroids, but they all look, kind of in a really bad position, and it still looks like we have bad clusters. So we're starting off with some, kind of nonsense clusters, but the hope is that we can continually iterate over these and make them better. And then what do we do after we compute these centroids? Well, we then assign observations to the centroid that is closest. So we reassign, right? And as we can see, even with our first iteration, right, we're actually able to get great improvement over the clusters that we have, even though these centroids were computed almost randomly, right? And as you can see now, just after one iteration of the k-means algorithm, we already have almost three distinct clusters, right? And you can see that in iteration one, step 2b, right? So this looks pretty good. And then what is the next step the algorithm do after we reclassify everyone to the closest centroid? As we recompute the centroid, right? So now you can see the centroids in iteration 2, step 2a. The centroids now move to the middle of each one of the clusters we have right now. And then we reassign again, right? And you can imagine this loop would keep going until these clusters stopped changing. But here it actually looks like it's pretty close to stopping, to not changing anymore. Maybe you can argue with me that some of these boundary cases should be in different places, but overall this looks really good, right? And how do we know it looks good? Because we can see that for any observation we take from one of these clusters, let's say any orange observation, they look very close to the other orange observations, but they don't look like the purple or the green ones, right? And similarly for purple and green, right? So this is a quite nice algorithm. We're going to learn how to use this in Radiant. So I'll switch over to my Radiant tab. So this is Radiant, as you've all seen before. I'm just going to use an example data set in Radiant. So I'll load these examples, and let's look at this toothpaste example that I showed you in class. So this toothpaste data set is just a survey given to a marketing agency where they asked each person in the survey 6 questions, and each question had a rating between 1 and 7, right? And these questions were supposed to help the marketing agency decide how to best market toothpaste to them, right? I know toothpaste is maybe not the most interesting thing in the world, but you can replace it with your favorite product, right? So for example, question 1 was that it was important to buy toothpaste that prevents cavities, right? Question 2 was how important is it that your toothpaste gives you shiny teeth, etc. Right? And let's say that we wanted to do market segmentation on this survey and decide how we can best market toothpaste to people, right? Maybe people who like toothpaste that can strengthen gums should get advertisements that talk about this, and maybe people who want toothpaste that gives them shiny teeth should get a different advertisement that talks about getting shiny teeth, right? So we can do this, and we can use the k-means clustering algorithm to help try to give us some natural groupings out of this. So to do that, I'm just going to go to multivariate, k-clustering, right? And then make sure here that the k-means algorithm is selected. And then, as we did before, I'm just going to select all the variables I want. So in this case, the 6 questions, right? And make sure that this standardize box is checked. You don't ever really want to uncheck it. The standardize box really just means that it's making sure that all the variables you're using in the k-means algorithm are comparable to one another. Because distance, when we're talking about distance in the k-means algorithm, right? If you have one variable that is sort of in units that are much different from other variables, or is much larger, right, then it's going to be really difficult to compare them in terms of distance. So this standardized portion just makes sure all the variables are comparable to one another when doing the k-means algorithm. And then we can determine the number of clusters that we want, right? Let's just start, let's say I want 10 clusters. Let's do something crazy. So let's say we want 10 clusters, because remember, we need to decide what k is ahead of time. And then I'll click Estimate Model. Great. So as you can see, the k-means algorithm is already done, and there's a lot of good information here, right? So it tells us that we generated 10 clusters, and it tells us the size of each one of the clusters. The first cluster had 8, next one has 2, next one has 4, right? etc. And for each one of the clusters, I can see what the average response was for each question, right? So the hope here is that if these clusters did a really good job, then the average response for each one of these questions should be quite different in each one of the clusters, right? So for cluster one, we can see that question one had an average response of 5.5, and in cluster two, it had an average response of 3. Those seem quite different, so that's not too bad. But if we go down here to cluster five, we see that it also had an average of question one for 5.5, which is the same as cluster one. So, okay, that doesn't make me think that these clusters are doing a really good job at distinguishing people. And we could do the same. We could do the same thing for all the questions, right? Maybe this isn't enough, right? Maybe we want to use other tools to diagnose how good this clustering algorithm is doing, right? And maybe we can use some of these diagnostic tools to help us decide on a better number for k. Right, so I'm going to go to plot here to go some more tools. Now let's look at some density plots. I think these are easy to look at. And this is sort of giving us the average response or the distribution of the response for each question for each cluster. Remember, I have 10 clusters. So for question one, I have the average response of all 10 questions. This is top left plot. And a lot of these distributions look really similar, right? So I'm not convinced that each one of these clusters is meaningfully different. In fact, if we look at question two, a lot of these distributions look almost the same. They're like overlapping. So I'm really not convinced that these clusters are actually giving us something that's meaningfully different, right? So maybe we want to pick a smaller number of for k here, right? And as we can see, we can go back here. I've sort of looked at this data a lot, so I'm going to tell you that my favorite number for this data set is 2. I think that's the best one. So let's redo it and just only do 2 clusters. And if we go back to this summary tab here, we can see that question one had a very different response average, right, for both the clusters. And going down through all the questions, we can see that these averages are quite different, right? And that's good. That means that the clusters seem to be giving us distinct information, right? They're not sort of meaningless clusters, right? And that's sort of our goal with K, is to give us a K that gives us meaningful groups, but sort of not a bunch of noisy groups and ones that make sense in the context of our business problem, right? So if we like K is equal to 2, that means we only need to do 2 different advertising campaigns, right? If I had picked 10 and I thought that all 10 were meaningful, I have to do 10 different advertising campaigns, which maybe has a different cost associated with it. So going back to these distribution plots, we can see that now for question one, the 2 clusters look very distinct. Similarly for question 2, they look pretty different, and going all the way down, all the way to question 6. So I'm quite happy with the way this clustering worked. And then if you want to add these cluster memberships to your data set, you can type in a variable. I'll say maybe k means class. Maybe you can give it something better, a shorter name that you can reference. Then you just click store, right? And then go back to your data set and you can see that now we have the k-means class in the data, right? And that's really it. A lot of what you're going to be doing is like fine tuning k, right? And trying to pick the one that makes the most sense, right? And the Radiant really will take care of everything else for you. So cool. And that's about all I wanted to talk about for this. If you have any questions about this or the case study we're using this more, please let